Hi everyone, my name is Giovanni Giustini. I am a lecturer in engineering simulation and data science at the University of Manchester. Today I'd like to give you a high-level overview of my research on boiling and its modeling with computational fluid dynamics. Now, before I break down the topics of today's talk, I would like to begin with some warm-up, some nice videos. So these are examples of my research. These are all animations from my research. And so in a nutshell, I do CFD simulations of fluid processes. So if we start from top right counterclockwise, we have bubble wall interactions, the modeling of surface effects on bubble behavior at the wall, typically in boiling, so both pool boiling and flow boiling, but also some other kinds of CFD that perhaps are a bit more familiar to us, such as, for example, the modeling of turbulent single-phase flows. So let me break down today's topic. Now, first of all, I'd like to give you a bit of context and motivation behind my research and talk about the bigger picture of this kind of CFD modeling of boiling, especially as far as the energy sector is concerned. Then I'd like to show some results from my career so far. Both are pertinent to the modeling of nucleate boiling phenomena, and both during bubble growth and the formation of some liquid films beneath steam bubbles growing at a wall, and but also some contribution in the area of boiling heat transfer. And after that, there is going to be what at least personally, I think is going to be, at least for me, the most interesting part of my talk, because I will show something that isn't really finished. And so hopefully that will be a good opportunity for discussion. And eventually some very preliminary conclusions and the wrap up of our chat. Now, okay, so boiling phenomena, as we know, are an integral part of energy systems. You just need to look at nuclear power plants, but in general, any power generation technology. Now that is rather clear to us in the multi-phase flow community, but outside of it, this isn't really appreciated. So a lot of academics coming from different backgrounds and doing different research, but still, for example, in energy systems, don't really appreciate the importance of boiling. And the default position seems to be that, that there is a saying that says that the steam engine did more for thermodynamics than what thermodynamics did for the steam engine. And it's since the days of what we have been boiling water to make steam. So this is all common practice. So why do we need to spend so much time in trying to understand water when it boils, when it turns into steam, and its behavior? So this is the context. Now, if again my research effort, both publicly funded and privately funded, is mainly funded by its main motivation is mainly its application to nuclear power, in particular hydraulics modeling of light water reactors. So if we stick to nuclear, okay, even maybe some nuclear people in the audience, yeah, okay, fine, but so why boiling in nuclear? I mean, we have most of the reactors currently operating in the world are pressurized water reactors, a PWR or PWRs. A PWR core works perfectly well with relatively fresh, not boiling, single-phase liquid water. Well, yeah, in principle, yes. In practice, there is some boiling in a PWR core as well. No net vapor generation, but there is definitely boiling in and rather vigorous boiling in the hot channel of a PWR. And but yet again, one may say, okay, fine, nuclear power, especially pressurized water reactor technology in nuclear power, has been around for ages, say 70 years. And we have been doing that without seemingly knowing anything about boiling. Safety seems to be guaranteed. Well, yeah, that's exactly the problem. So safety seems to be guaranteed, but at what cost? So 70 years of increasingly expensive nuclear power, at least in the West. So the idea is that, okay, fine, one way to look at it, maybe there is a lack of fundamental knowledge of the basic fluid processes, whether it's kettle boiling or nuclear reactor boiling, it's the same, still not very well understood. That is one of the causes of significant conservatism in analysis and design. And we need to ensure safety at all costs in nuclear, so we need to have large safety margins, which can be thought of as one, at least, of the principles of the huge cost of nuclear, at least in the West. And I mean, obviously, this is one way to look at it. Someone else work in different disciplines, for example, non-destructive evaluation or structural integrity. They may say, yeah, okay, I mean, that's surely one reason, but at the end of the day, we need to have strong pipes and strong pressure vessels. So maybe it's not really boiling. Maybe it's it's some other kinds of considerations. Okay, that may be, but I'm a multi-phase guy. I do boiling, so I think that this rationale seems at least a plausible excuse to do some good science. So what kind of good science do we want to do? So my specialty is actually numerical simulation using techniques based on computational fluid dynamics. And the idea of a rather high-profile research effort that I'm involved with, funded both by the UK taxpayer, via the Engineering and Physical Sciences Research Council, and by sponsors such as my main sponsor from the industry, Rolls-Royce Nuclear, is that, okay, we can have a combination of very detailed, and I explain in a moment what kind of detail I mean, very detailed physically based fundamental simulation going in parallel with experiments for verification and validation. This gives us a good understanding of the basic processes involved in boiling, so bubble growth, bubble departure, bubble rise, boiling heat transfer, and so on. So with a combination of these two aspects, we can generate a decent amount of data to train the next generation of data-driven modeling for more accurate analysis, say more, not really at the small scale of single bubbles, but more at the component scale of, for example, a nuclear fuel channel, or at the system scale of the core itself and the rest of the plant. So the idea is that, okay, it would be good if there were, if as a consequence of all this number crunching and modeling the little bubbles and so on, there would be a technological breakthrough that would enable us to quantify fundamental fluid processes, not just boiling, but then maybe also single phase flow, turbulent heat transfer, and so on. So generate and assimilate sizable amount of high quality simulation data. And as a consequence of the understanding that we can gain thanks to the data, reduce conservatism in the modeling and design approach in nuclear, so that at the end of the day, we need to still guarantee safety, but eliminate reliance on safety margins, which generate huge costs, and at the end of the day, drive down cost of current water-cooled nuclear, at least in the West, I would say. Then, in other parts of the world, there are other considerations, and maybe this rationale wouldn't really apply. Now, where are we? So we have an excuse to do something that I believe is interesting and can be, at the end of the day, an advancement of the state of the art in multi-phase flow and boiling. What kind of weapons do we use to tackle these huge problems and to fulfill this promise of learning a lot about boiling, especially in a nuclear context, and driving down the cost of nuclear? Now, the kind of CFD that I use is maybe not the usual CFD we're accustomed to, and I use interface resolving techniques for two-phase flow. And these are called interface capturing methods. And the basic idea is that with these methods, we want to model the transition region between two fluids and approximate it on a finite volume numerical grid. So, for example, the interface can be the curved surface of a bubble growing at a heated wall. So this is the methodology that underpins the physically based fundamental simulation that me and my coworkers use. Now, these interface capturing methods are coupled with the ordinary CFD simulation methodology, the same that we use for flow water in a pipe, aerofoil, Formula One car, and so on. And with this interface capturing, we can detect where the two phases, for example, vapor liquid, are, what is the interface doing through time. And as we can see from the image of this triangular mesh at the center of my slide, it is really the case that all the action is in only a few cells where my liquid changes into vapor. And so from the point of view of continuum mechanics, is a waste, really. But we shouldn't be fooled by this aspect, because in reality, this narrow band of cells where my liquid turns into vapor, in reality, it's a whole world apart. So if we were doing molecular mechanics, that would be basically all that we are looking at in terms of our simulation domain. So that's the tricky bit of interface capturing. We have something rather complex, and we need to capture it on a handful of cells in our simulation domain. And by the way, the mathematical trick to do that is basically to capture the interface as a smoothed step distribution, where I have a function that indicates my two phases that varies smoothly from one phase to the other. Say typically we have our indicator, which is 0 in the vapor and 1 in the liquid. We have 3 cells where a smoothed step distribution changes from 0 to 1. And with this trick, we can model all the relevant interfacial physics in a rather straightforward way. So with this rather simple concept, but of course implemented in a kind of, I would say, in a non-trivial CFD framework, the same that we use for applied simulation in engineering, there are a number of things that we can look at in boiling. And I would like to start with the so-called micro layers. Now, we would expect normally that in boiling, say, boiling of water, full boiling of water at atmospheric pressure, we would expect that the solid surface exposed to the vapor inside is exposed to the vapor inside the bubble. That's what we would expect. Well, things are not really this straightforward. So these images are from my coworkers in Korea, the group of Professor Hyundai Kim. And so here we're looking at single bubble growing at a heated surface. So we have the top row of images is the side view of the bubble, so just seen from the side, and the other 2 rows of images need a bit more of interpretation. So the middle row of images represents an interferometric detection of liquid beneath the bubble. So there seems to be a liquid film beneath the bubble that, when we use interferometric measurement techniques, shows us an interference pattern, some fringes. And this is at least what appears to be from experimental measurement. And actually, some other measurements from the lab, the last row of images. Now, this is an infrared measurement of the temperature distribution at the solid surface beneath the bubble. So red means hot, and then from yellow to green to blue, increasingly cold surface. Now there seems to be something. There seems to be maybe some entity, possibly a liquid layer, or in any event, there seems to be something that is evaporating. And we are relatively confident that what is evaporating is a very thin layer of liquid, the micro layer, that is left behind on the solid surface during the early stages of bubble growth, and then starts to evaporate, and eventually, when the bubble is grown up later on, disappears. But we'll get there in due course. So this is a sketch of what is likely to be the typical shape of a microlayer beneath a steam bubble. And this is what we would see if we were some kind of Laplace demon sitting on the solid surface. And actually, we generated this image with computational fluid dynamics. The important point to bear in mind is that these layers seem to be really, really thin. So they are something like 5 microns in thickness, but they extend radially outwards from the center of the bubble base up to a few millimeters, so extremely shallow. Now, the idea is, okay, fine, we know something from the lab, but what can we do with CFD? And with CFD, we can do something that was actually pioneered at MIT by a colleague of mine from the US who was working on his PhD more or less when I was doing it, Dr. 𝗪𝗪𝗂𝗁. And so the idea is that we can use hydrodynamic interface capturing simulation to inflate a bubble and study the formation of the microlayer beneath the bubble. So this technique was pioneered over there at MIT using computational tools conceived for research. So me and coworkers, formerly at Imperial and now at the University of Manchester, are using a similar methodology, but implemented in more broadly applicable CFD toolboxes, such as, for example, 𝗪𝗪𝗂𝗁𝗪 and 𝗪𝗵𝘁. So in these videos here, we are seeing results of a hydrodynamic simulation of microlayer formation with 𝗪𝗵𝘁. And the blue is the liquid, the white is the bubble, that is to say, the vapor. In the bigger video, I have included some arrows that represent velocity vectors at the interface and in the liquid, and the close-up represents the hydrodynamic process of microlayer formation from a qualitative point of view. The important point here is that there is, at the base of the bubble, there is indeed a point where the liquid ends, which is, if you can see my hand or arrow here, there is indeed a point where the liquid ends and the vapor begins. That's the inner root, let's call it like that, region of the microlayer. That is what in the academic community we call the triple contact line. One of the important points of these simulations is that the triple contact line stays there as a consequence of the solution of the basic transport equations. So there are no artificial means in the simulation methodology to keep the triple contact line pinned at the inner end of the liquid film. With this trick of inflating a bubble artificially and then looking at the hydrodynamics, we can actually get some decent results when compared against the experiment, at least during the early stages of bubble growth. So the idea is that we studied the hydrodynamics because we believe that the hydrodynamics only simulation of a microlayer is representative of a very early stage during bubble growth, during which the layer hasn't had the time to evaporate due to the transport of heat from the solid surface. And here, just an example of the results that we can get. So these two images, these two plots have been plotted at 2 different times into the simulation. And the various lines are simulation results, and the black hollow squares are experimental data from Professor Kim's lab. And so qualitatively, the agreement seems to be all right. However, this work that we did a while ago, and a follow-up is going to appear at the ICMF in Kobe, actually ended with a question mark that we are trying to address right now with colleagues at Imperial College, actually, the group of Professor 𝗪𝗁𝘁. So the point is that it looks like the shape of the microlayer depends a lot on the wettability of the surface, as embodied in our computational model with the input contact angle indicated here as gamma that we give to the model. This is a bit of a quandary because we seem to be getting best agreement between model and measurement for a contact angle close to 0, whereas we know that normally boiling at the surface on ordinary surfaces, we have contact angles between, I would say, 40 and 90 degrees, something like that. So here, this is a validation exercise in conditions of �𝗆·𝘂𝗁𝘁 experiments. And they indeed measured static contact angles on their boiling surfaces, and these were close to 65 degrees. However, if we input a contact angle of 65 degrees in our computational model, we don't even get a microlayer. So huge question mark, and there will be a follow-up to this at the multi-phase conference in Kobe next year. And so between now and the Kobe conference, hopefully, me and colleagues from Imperial will have something more to say about this. Okay, so this was one possible example of applications of interface capture in CFD to modeling some aspects of boiling phenomena that we believe are important. Later on during bubble growth, of course, we know that a bubble grows at the surface during boiling, but eventually departs and goes into the liquid. And if we're looking, I don't know, at convective boiling, is then advected away into the flow. Anyway, so the microlayer is not all that there is to say about boiling. And there is another topic that I find particularly interesting, and I'm glad to be presenting some results to you about it. And that is the study of boiling heat transfer at bubble departure. So once the microlayer has formed, it has then evaporated, it's gone, it's disappeared. Well, there is still some time left in the life of a bubble before it departs from a surface. Now, I like to call this the Griffith problem, and in memoriam of the late Professor Griffith from MIT, who was the first to introduce and study the problem. And the idea is that we want to study what happens when a bubble departs in terms of quantifying the flow of heat to cold fluid attendant upon bubble departure. And here the idea is that what we have at the surface is that first we have a bubble, then due to gravity, the bubble disappears from the surface, but the volume of space previously occupied by the bubble due to continuity needs to be replaced by something. And this something is the surrounding liquid. Now, if my liquid comes from sufficiently far away from the surface, the chances are that it's a bit colder than the solid surface itself, which means that likely there is a flow of heat from the solid surface and this new cold fluid put in contact with the surface. So the problem was the question is, of course, fine, okay, but how important is this? We know that there is latent heat transfer due to bubble formation. Give or take, it's in the region of a few millijoule per bubble, at least in atmospheric boiling of water, pool boiling conditions. And I mean, okay, is that important? Is this Griffith flow of heat comparable to the latent heat transfer of bubble formation? And the answer is actually yes. So that's the reason that some millijoules of heat flow are involved also when this kind of single phase heat transfer mode is taking place. So it's important to study the problem. And the original Griffith model assume the constant temperature solid surface, bubble size at departure, and liquid temperature. And nowadays, with computational fluid dynamics, we can build more elaborate computational models. So first of all, we can calculate the bubble size and the liquid temperature around it directly via post-processing simulation results. And these kinds of simulations also include conjugate heat transfer. So from the solid side of the solid fluid interface, we can actually directly extract from simulation the instantaneous behavior of the heat flux distribution at the solid surface beneath a bubble. And this is more or less what we get for this kind of problem. So this is a study both with CFD and with experiment of bubble growth and departure during pool boiling of water, in this case at atmospheric pressure. Again, 3 rows of images. Top row of images is a side view of the bubble as modeled with CFD. Middle row of images, phase distribution on the heat transfer surface from CFD. The red ring is where basically the microlayer is before it evaporates. Too long to go into details, but in this particular simulation, we are not really resolving the microlayer with a computational grid. There is an algebraic offline model that takes care of it. But the bottom line is that once this model decides that there is no more microlayer, then the behavior of the bubble at its base is handed over back to the CFD. So it's again fully resolved by the computational grid and fully mechanistic. The last row of images, it's again the interferometric measurement, again from our colleagues from Korea, that shows initially a fringe pattern, so presence of the liquid, but eventually the disappearance of the liquid. So after the vertical solid line, what both experiment and CFD simulation tell us that at the base of the bubble, there is a broadly circular area of solid surface which is exposed to the vapor in the interior of the bubble. And as the bubble is departing, this circular, approximately circular area, this approximately circular dry patch actually, is shrinking, and as it does so, there is an advancing liquid front that re-wets the previously dry patch, likely giving rise to heat transfer from the solid surface to the fluid. And this, we can call this a re-wet process. Then after the bubble has departed, again, I just have likely fresh liquid in contact with the surface, and there is a heat transfer mode that we can broadly characterize as a quench or quenching heat transfer. And again, from the lab, we do indeed have direct measurements of the heat flux, of the planar distribution of the heat flux at the solid surface beneath the bubble, without going into details about the experimental technique used by our colleagues. The bottom line is that from direct measurements of the temperature of the solid surface, we can actually reconstruct the corresponding heat flux on the solid side of the heated surface, and from that we can extract radial or transversal profiles of the heat flux at the solid surface, both during, and here I'm looking at the images on the left, both during this liquid re-wet process and also during the subsequent post-departure quenching process. And give or take, what happens is that the magnitude of the flow of heat can be initially quite considerable. We have something like 150 kilowatts per square meter, which is not as bad a heat flux, which then decreases with time. So we can use this data for a direct comparison with simulation results, which is done here on the right-hand side, where we have the same plots, so distribution of the heat flux on the solid surface, versus radial distance from the center of the bubble base during the wet period, during bubble departure, and during the quench period after bubble departure. And we could get what I believe is most likely a fluke, an agreement which is possibly too good to be true, but there you go. Was good to see this. So good agreement between CFD and an experiment in our estimates of heat transfer and bubble departure. And what's more, it is actually with modern present-day sophisticated CFD techniques. Okay, we can get the numbers, lots of number crunching, so we can get our spatially varying and temporally varying heat flux distributions, but we can compare that also to predictions of the original heat transfer model of bubble departures or re-wet and quench heat flux. And the bottom line is that, okay, let's have a look here at the image on the left. So we have a solid line with different colors. These are simulation results, and the different colors correspond to different time into bubble growth. So we have, into bubble departure. So we have the sequence goes from green to black to gray to purple as we go into the re-wet and quench process. The colored squares are direct measurements of the heat flux at the same times, and the dashed lines are an evaluation of the spatial distribution of the heat flux according to the original heat flux model, heat transfer model at bubble departure. And one of the conclusions was that actually the order of magnitude of the heat flux predicted by the original model by the late Professor Griffith and co-workers was remarkably accurate, at least in terms of the order of magnitude of the heat flux. So that is a pretty remarkable result that it took a while and lots of CFD to confirm. However, due to neglect of conjugated transfer in the solid beneath the bubble, there was a bit of an estimate, especially during the early stages of re-wet, of the actual precise magnitude of the heat flux. But still, a very accurate pen and paper model. And so only with generally applicable CFD we could get something similar. And another aspect that it was possible to elucidate with CFD is that another of the physical phenomena that were postulated early on was some kind of scavenging effect by a growing and departing bubble on the temperature distribution near the wall. So locally, removal of hot liquid and arrival of relatively colder liquid from the surrounding area around the bubble base, and which is something that actually the temperature distribution from CFD simulation confirmed. So here, if you can see my arrow, there is indeed what looks like a tongue of liquid, or relatively cold liquid, and surely colder than the solid, which is below the black line that is actually cooling the surface. So qualitative physical phenomena originally postulated with a pen and paper analytical heat transfer model could be confirmed with CFD, which to my mind is a rather compelling evidence of the power of present-day CFD with interface capturing in tackling these kinds of problems. Now, these are not the only problems that we are looking at. There are other activities going on, and I'm beginning to realize that I do not have much time, so I'm not going to rush, but I hope that I won't leave out too important details. Now, another open challenge in modeling that I'm very interested in is that of microlayer evaporation. So let's recap a little bit what's the situation right now. From a modeling, on the modeling side, thanks to a sustained effort over quite a few years, I mentioned early on work at MIT, but the problem was tackled also by some colleagues of mine at Imperial College London. So on the hydrodynamic side of things, we can get good predictions of the hydrodynamic process of formation of a microlayer beneath a bubble. And however, the problem is that on the right-hand side, we are looking at the temperature distribution, and there is something that we can't capture with the hydrodynamics. So the thing is that the microlayer is evaporating more or less as it forms. It also evaporates on a solid surface. And proof is the temperature distribution at the solid beneath the microlayer. So we have a ring-shaped temperature distribution with a cold ring-shaped solid region, which is suggestive that this layer is sucking heat from the surface because it's evaporating. So you can imagine that there is a heat flow on the vertical direction going through the microlayer that is driven by the temperature difference across the layer between the solid surface, that is the bottom surface of the microlayer, and the upper surface of the microlayer, that is the vapor-liquid interface. Now, this is rather evident from experiment, but from a modeling point of view, we're not very good at doing the sums and actually estimating what's going on. Anyway, let me explain. So here are some results from a work that we did in collaboration with Korea, again, with Professor Kim, and let's have a look. What do we have? So at the center of my slide, the bottom image is a direct measurement of the film thickness versus radial position on the solid surface. These are the hollow purple squares. The top graph represents, on the left, the heat flux at the solid surface, and on the right, the temperature distribution on the solid surface. And by the way, this is a transient, is a time-dependent process. So here I'm showing only estimates of the various quantities at one particular instant of time into microlayer evaporation. So what we have here are the blue circles represent the instantaneous radial distribution of the temperature at the solid surface, showing a rather evident cooling effect, most likely due to microlayer evaporation. The red and blue symbols, blue diamonds and red circles, represent quasi-direct measurements of the heat flux of microlayer evaporation. And here I have plotted results from Korea, but at the same time, there have been similarly consistent measurements both from MIT and IIT Mumbai that show a very similar distribution of the heat flux on the surface. So a flat heat flux distribution. Okay, fine. What is the problem? The problem is that all theories that we have, whether they are pen and paper calculations or very sophisticated molecular models of an evaporating liquid film with its vapor-liquid interface, tell us that actually we should expect a much larger value of the heat flux as the film thickness goes down and we are approaching the end of the layer. So the curly bracket that I have indicated here indicates this huge anomaly, this huge mismatch between our best understanding of the evaporation process and the available measurements, which suggests that likely there is something going on with our evaporation process. There seems to be an additional resistance to the flow, to the evaporative flow of heat, which we normally call an evaporative thermal resistance, that effectively limits microlayer evaporation and the corresponding heat flux. Now, the good news are that, okay, our representation of interfacial evaporation is imperfect at best. But the good news is that, okay, can't we use the CFD to predict film behavior, microlayer behavior mechanistically from first principles, and then use that as a vehicle to test our different theories about evaporation? And this is what we're actually trying to do with Mirko Magnini, and a PhD student that we are supervising at the University of Manchester. So what we're trying to do is basically all in. We use CFD to do hydrodynamics, heat transfer in the liquid and the solid, contact angles, modeling of the mechanistic modeling with suitable correlations of the evaporation at the vapor-liquid interface. And this is most likely the only way to crack the problem. And by cracking, I mean that, okay, so we can look at the bubble as it grows on the surface. We can model the hydrodynamics of the microlayer. So via tuning the various empirical constants that appear in our very approximate evaporation models, we can actually get a ballpark estimate of what are likely the evaporative heat transfer coefficients, both at the curved surface and at the microlayer, that give us good agreement with experiment. And that at least give us, some more indications at what could be the likely cause of the anomaly that we just saw in microlayer evaporation. And so this is again a close-up of microlayer formation and evaporation using CFD. The black line is again the solid fluid interface. So we're doing conjugate transfer. We are actually resolving the temperature distribution in the liquid around the bubble, but also in the layer itself and in the region in the region where the layer is just beginning to appear. So early days, and we're talking about simulations that luckily we can assume that our bubbles are rotationally symmetric, so we can use two-dimensional axisymmetric simulation. And nevertheless, we have many cells, and due to some numerical restrictions on the values of the time step, we need to use very small time steps. And so at the end of the day, they are not so quick at running these otherwise not too heavy CFD simulations.
Giovanni,
yeah,
we have approximately 10 minutes left, and I want to make sure we have enough time for question. I don't know how much.
2 slides.
Okay, thank you.
Thanks, Matteo. Okay, another aspect that we're looking at right now is actually flow boiling in subcooled conditions. So when we have that the liquid is a bit colder than saturation temperature. Here is work again in collaboration with Korea, and there are preliminary results. We are running CFD in conditions of a recent set of measurements where we are looking at single bubble behavior in flow boiling in subcooled conditions in a mini channel with X-ray. So here we can't see very well, but there is a little ghost of a bubble and measured, and its appearance is detected with X-rays. So here there are basically 2 research questions that we're after. Okay, first of all, we need correlations to capture evaporation at the surface of a bubble. But does the model that we have for evaporation work also for condensation? We don't know. We're trying to find out. And likewise, again, weightability and likely values of the contact angle of the surface seem to be, again, important in determining bubble behavior. And lastly, what we have seen so far is actually simulation on rather simple geometries, so without taking into account surface features. However, we know that in boiling, surface features are important. There is this story that we need a cavity or a notch on a heated surface to initiate and sustain boiling at ordinary temperatures. Here, in reality, we are looking at bubble growth at cavities that are a bit larger than the cavities that I have just mentioned. I can't give the exact numerical details of what kind of cavities we are looking at. There is involvement of an industrial sponsor in these kinds of projects. But anyway, the bottom line is that, okay, fine, let's take our interface capturing CFD methodology and let's try to implement it in general applicable open source toolboxes such as 𝗪𝗺, so simulation on arbitrary meshes to tackle boiling boiling problems on arbitrary geometries. And so far we got to the stage that we could validate the methodology using standard test cases for free bubble growth and rise away from surfaces, but using the same CFD methodology that we then used for bubble growth at a cavity or at a notch. We got rather reassuring results in terms of bubble radius versus time for a rising bubble, provided that we use rather fine meshes. So here we're talking about millimetric bubbles, and we need to resolve everything with meshes with cells that are something like a few microns in size. So again, numerical challenges. And all this is to look at wall boiling in the presence of a surface structure. And then with that, yeah, 45 minutes. I think I've been going on for long enough. And any questions? Okay, I would summarize what I have just said in the following way. Okay, we can, yes, I hope that I have given an indication that we can use computational fluid dynamics to support industrial applications such as thermal hydraulics and boiling for nuclear power, industrial applications that rely on boiling. We can indeed model in detail key local physical phenomena during boiling at the surface. And for applications, we can explore the effect of parameters believed to be important in certain applications of boiling. And here I made an example. Okay, we have an interest in surface structure for nuclear applications, and we use CFD for that. And with this, I shut up. Sorry, I'm a bit late. Delighted to take any questions.
Thank you very much, Giovanni. Really insightful presentation, and I'll open up to questions. I see already that Said has his hands raised. I suppose you have questions, Said?
Yes, Giovanni, my experimental results that involves direct measurement of the heat flux when the microlayer forms is very much consistent with your simulations. I even back calculate the Matteo. Can I share just one graph with you?
Yeah, of course.
If you're in, can you?
Yeah. So this is the graph. So basically, these are sensors that I can show you that directly measure the heat flux at the interface, and this is due to microlayer evaporation, and the heat flux that it generates is much higher than the average heat flux. As well as the heat flux during the due to liquid rewetting, which is liquid rewetting. So I'm a little bit surprised with some of the experimental results that you were comparing with other groups. There is no physical phenomena that impedes evaporation of, and actually when we back calculated the amount of heat flux, thickness, we came down to 3 to 5 micron, which is very consistent with some of the other numerical results that you showed. And there is no phenomena that impedes that evaporation until you maybe go to nanometers. And the measurement was done through these multi-layer temperature sensors and radially. And basically heat goes through these and we measure the delta T and heat flux. So I thought that your numerical results are spot on.
Okay, thank you. Yeah, thanks. Looks good. Maybe the fluid is different, but we can, on a computer, we can change the fluid easily.
To follow up on Said's question, if you look at the evaporation coefficient, I think that's where most of the empiricism it is at this point, right? Because you have experiments that give you values that are 1, 2, and even 3 orders of magnitude smaller compared to molecular dynamics. Yeah. And I honestly, as an experimentalist, have serious doubt that the infrared experiments conducted by myself as well have the precision to make that, measurement. At least in the kind of experiment you mentioned, a nucleate bonding with very, very short time scale and length scale. but it's indeed a very open question. So the question I have for you, Giovanni, very quickly is, what sensitivity do you have to the evaporation coefficient?
Huge. Huge. So it's that confirms exactly what you have just said, and I believe we either believe the experiment or we believe the theory. I am a modeler, so I should believe the theory, but I always believe the experiment. So again, there's a quandary again, but yeah, there is a huge sensitivity. So the evaporation coefficient is basically is an as yet unknown coefficient that basically tells us how vigorous evaporation at the upper surface of the microlayer is, and depending, and it can be anywhere between 0.01 and 0.99. Theory says it's close to 0.99. Pen and paper calculations done using the measurements that Matteo mentioned gives us an estimate closer to 0.03. So open question, but I do agree that measurements, especially this kind of sophisticated infrared, needs to be handled with care.
Yeah. Vladimir, you have a question?
Yes, just to continue this discussion about the microlayer. So I think, this idea that evaporation becomes very strong when the thickness goes down is ultimately based on the assumption that the interface temperature is close to saturation and the substrate temperature is substantially different from that. And so both of these assumptions, in some experiments may not be valid because, for example, depending on conductivity of the substrate, it may be that, there's a lot of cooling of substrate. And then also the equilibrium temperature at the liquid vapor interface is different also from the kind of standard value at intense evaporation. So I think both of these things could happen. I would be very interested in learning more about those experiments where you show that the flux is, almost constant. I mean, it's a bit of a surprise to me. Maybe you could say a little bit more about those, but I think they could be explained by these arguments.
Yes. So let me answer your question very briefly. So you mentioned the thermal response of the solid and the fact that the solid surface temperature changes. The temperature in the interior of the solid changes. We can do that with CFD, and we are doing that. And also, when post-processing the measurements from our colleagues, we did include that. So both in the latest CFD simulation that I have shown, with the full bubble plus the solid, and also in post-processing data from Professor Kim, we did include the cooling of the solid. So that is one variable that we included in the model. And there is massive cooling in the solid beneath the microlayer. And by the way, not just during the microlayer, because also during the bubble departure, conjugated transfer is important to get the numbers right. So yes, I agree 100% with both your suggestions. So we took care of the first one, the second one, not entirely sure what's going on.
Okay, we actually have a question on the chat by Anton. I don't know, Anton, if you want to unmute yourself or you prefer me to ask the question.
Matteo, thanks. Giovanni, thanks for the nice talk. I would like to ask you several questions. In reactors, we deal with the high pressure, and have you simulated the evolution of the microlayer during boiling at different pressure? Because we know that the bubble dynamics is technically different for different pressures. And what effect do you think the pressure will have on the heat transfer in the microlayer region? Thank you.
Right. So I didn't have to do that because, and I could focus on atmospheric pressure because some colleagues of mine did that already and conclusively demonstrated that there is no microlayer at high pressure because bubbles do not grow fast enough. So all other things being equal, say at the same wall temperature and at the same temperature of the liquid where the bubble grows, at higher pressure, the density difference between the liquid and the vapor is much smaller than atmospheric pressure. So for unit of slice of liquid that we are removing, we are generating a vapor phase that is not as rarefied, so it's denser, so it inflates the bubble a lot less. So the net result of this is that bubbles grow much slower in reactor conditions, and the fluid reaction forces that at atmospheric pressure cause hemispherical bubble shape and microlayer formation are not there. So there is no microlayer formation. So this was a given of all our analysis. When we do high pressure bubbles, well, there are other challenges, but we always get almost spherical bubbles barely touching the wall, and they are not pushed against the wall, and therefore there is no microlayer.
Thanks. Can I ask you another question? I see that in your calculation simulation result, the boundary between the dry spot and the liquid is not moving, doesn't moving, and in reality, the microlayer evaporates during time, and the boundary between the boundary of the hot spots is moving. And do you realize it in your simulation result?
Yeah. So now one of the penultimate slide, or the one before, there was a video of the work that we're doing now. So in that one, results still need to be improved, but we are seeing that yes, the layer begins to disappear close to its inner edge, and then the triple contact line moves outward. So yeah, we're expecting to see that.
Thanks. Nice talk.
Giovanni, is it okay if I share on the chat your email address so that people?
Yeah, sure. Yeah, absolutely. Because we're running late. Sorry.
So this is Giovanni's address. So if you want to ask more questions and comments, feel free to contact Giovanni at this address. Okay. Well, with this, I think we're out of time, and I want to acknowledge. Thank first of all Giovanni and all of you also for attending this meeting. The next talk will be on December 16, if I'm not mistaken, so right before Christmas, and will be given by Professor Antau from Texas A&M. With this, thank you again, Giovanni, and yeah, have a great rest of the week to all of you guys.
Pleasure. Many thanks. Bye-bye.
Bye.
Cheers.